Hello, everyone, and welcome. My name is Luca Hernandez Acosta. I am a PhD student at the University of Göttingen, working at the Institute of Computer Science, more specifically in the research group for computer security and privacy. And today, I would like to present to you my paper, Does Cycling Reveal Insights About You? Investigation of User and Environmental Characteristics During Cycling. Before we go ahead into the presentation, I would like to give a brief overview about the content that we are going to talk about today. First, giving a brief introduction to the topic, then some related work, afterwards some methodology and the approach that we have used before coming to the results that we have obtained, and afterwards giving the limitations as well as an outlook into future work. And finally, concluding our topic with a brief conclusion. Well, the use of smart devices, for instance, smartphones and smartwatches, has increased in the last few decades. And this is probably also because those devices provide for easy communication and also access to information located on the internet. Further, those devices are equipped with various sensors, opening the room for new application areas, which further increases the popularity in the areas of fitness and health tracking. To provide such a service, sensor data is collected and analyzed, and often this collection and analysis takes place on servers maintained by manufacturers and developers. Especially the movement data is collected for fitness and health applications in order to, for instance, count the steps or analyze the walking behavior. The analysis of such data, however, poses risks to the privacy of an individual user, because we can recognize certain activities, not just the walking, the running, but also eating, writing, or maybe even the typing on a keyboard. Further, we can use those unique movement patterns in the sensor data in order to identify users, for instance, based on gait recognition. And beside those activity recognition and user identification, we further can infer personal characteristics such as age, gender, and health status. In this study, we aim to investigate cycling data that is generated while riding a bike, and the potential of these data to infer certain characteristics. The characteristics that we have observed can be divided into 4 dimensions: bike type, gear, seat height, and Tehran. We have selected alternatives for the bike types: the road bike, mountain bike, gravel bike, e-bike, the gear 15th and 21st gear, the seat height set to low, normal, or high, and the Tehran for dirt road, bike road, stone road, and asphalt road. Beside those characteristics, we also conducted a user study with 17 participants to explore the potential of this data to distinguish between different participants. Coming to the related work, the related work can be split into the categories of activity recognition and user distinction. It has been shown that different activities such as walking, running, eating, or writing can successfully be determined. And further, the movement data can be used to identify users, for instance, in gait recognition. Matkovic and further authors show first approaches to identify different bike types and also e-scooters. However, in contrast to those existing studies, we also examine characteristics other than just the bike type and consider smartwatch data in combination with smartphone data instead of just relying on the smartphone data itself. When it comes to the methodology and the data collection, the devices that we have used in order to collect the data is first a smartphone, a Google Pixel 4, and a smartwatch, a Samsung Galaxy Watch. The sensor was collected at a frequency of 400 Hz and 100 Hz, respectively, to the smartphone and the smartwatch. The smartphone was placed always in the right pocket of the trousers, upside down with the charging port at the top and the screen facing away from the body. The smartwatch was always worn on the right wrist. Our study design looked as follows. We first collected a dataset by a single person among the 4 dimensions: bike type, gear, seat height, and Tehran. And we performed a second user study with 17 participants of which were 10 male participants, 7 female participants, between the ages of 19 and 64. All participants had to ride the same bike on the same bicycle road for approximately 2 kilometers. And only the seat height was adjusted. The gear was always set to the 15th gear. Our approach that we have used was inspired by some of the gate-based related work that used the gate in order to recognize certain users, and was based on the identification of certain repetitive patterns. And such a repetitive pattern, in our case, was a single pedal rotation. And in order to detect such a repetitive pattern, we were left with different approaches to detect pedal rotations. First, by using the minima, the maxima, or the turning points around the zero value. For our case, it turned out that the turning point approach worked out best. However, for some participants, the X values tend to oscillate around zero. And to fix this problem, we used the Z values and the X values in combination in order to detect such a pedal rotation. To extract the features, we had, first of all, to make all pedal rotations comparable to each other. And the approach that we used in order to make these pedal rotations comparable was by utilizing a binning approach, where each pedal rotation has the same amount of bins. And then we calculated the timestamps according to the number of bins. And when mapping certain sensor readings to those bins and the timestamps, in some cases, we had to make use of linear interpolation for those timestamps that have no accurate accelerometer or any other sensor data available in our dataset. And while using linear interpolation, we were able to calculate this appropriate accelerometer reading for a timestamp or the respective bin. Further features that we have are the maxima, the minima, variance, and the standard deviation that we will take into consideration for the later classification steps with machine learning. To find the optimal number of bins for our classification algorithms that we have obtained, the Gaussian naive Bayes, k-nearest neighbors, linear support vector classification, decision tree, and random forest, we decided to put the rate of correct predictions in relation to the number of bins and increase the number of bins and observe the correct predictions. We found that with an optimal number of 40, that most of the classifications reached their top performance, while after an exceeding number of bins higher than 40, the performance declines. At this point, we want to highlight that this optimal number might be optimized when taking into account even higher number of bins, but for our approach and our use case here, it was enough, and sticking with 40 as an optimal number was sufficient. Looking at the results with the characteristics first, looking at the bike type, we observed again 4 bike types: the road bike, mountain bike, gravel bike, and dirt bike, and we achieved an accuracy of 93.05% with the random forest classifier while using the smartphone and smartwatch data in combination. When taking a look at the confusion metrics and the values of precision, recall, and F1 score, we do see that the e-bike, or the classification of the e-bike, performed best, while the gravel bike classification was worst. And this might be also the case because we have, if we look into the confusion metrics for the gravel bike, we have slight confusions with other classes, which also result in the precision and recall being lower than in the other classes. For the gear, we have observed 2 gears, again the 15th and the 21st gear, and we were able to achieve accuracies of 92.23%, also with the random forest classifier, and also with the smartphone and smartwatch data in combination. Taking again a look into the precision, recall, and F1 score, as well as the confusion metrics, we do see that the classification of the 15th gear slightly performed better than the 21st gear. When it comes to the seat height, first of all, a little bit more detailed, we calculated the seat height according to the distance between the center of the chain set and the top of the seat, resulting in low for 60 centimeters, normal in 85 centimeters, and high for 95 centimeters. And the highest accuracy of 95.76% was also achieved with the random forest classifier, also with the smartphone and smartwatch data in combination. However, we do see that the smartwatch data reduces accuracy for some of the classifiers. If we look on the right-hand side, where we only have the smartphone data available for classification, we do see that the KNN classifier with just the smartphone data performed best than with the smartwatch data in combination. When taking a look into confusion metrics, the precision recon F1 score, we do see that the low seat height performed best in terms of classification, and that the normal seat height performed worst. And this can also be brought back to the fact that the normal seat height often got confused with the different classes of low and high. Coming to the terrain, we observed 4 terrains: the dirt road, bike road, stone road, and the asphalt road, and we were also able here to achieve accuracies of 94 to 24% with the random forest classifier. Here also the smartphone and smartwatch data in combination showed the best results. However, we want to highlight that the smartwatch data increases accuracies for all classifiers. When taking a look again here at the table at the bottom right, where we only have the smartphone data available, and take a look at the random forest performances, we do see that in combination with the smartwatch data, the performances increased. Also, looking at the confusion metrics, precision recon F1 score, we do see that the classification of the bike road performed best, while the dirt road performed worst. Coming to the user study, again, we observed the data of our 17 participants, and we have observed accuracies of 99.01%, also with the random forest classifier. And also smartphone and smartwatch data in combination showed the best results. However, we want to highlight that the smartphone data alone is also sufficient in order to classify or identify the different participants. Here again, an overview about the confusion metrics as well as the precision recall and F1 score. And we do see that overall we have quite promising results in order to basically distinguish between different participants. Coming to the limitations and outlook, we only had a user study with 17 participants, and a higher number of participants might decrease the accuracy. So for future work, it might be of interest to look and redo the study with more participants, collect more data, and then afterwards analyze if this changes anything with the results obtained for the user study and the distinguishment. The location of the smartphone could also be changed. While currently we have the location in the trouser pocket, we could change the location to the back pocket or a backpack or any other usual location where smartphones are located. And then afterwards look on the results obtained from different locations. Further, when it comes to the terrains, we have only observed terrains with no inclines or very slight inclines or declines, while it would be interesting to see if terrains with different inclines and declines might produce different results. While this study focused on the feasibility to differentiate between different users while riding a bike and also identify certain characteristics, we want to further highlight that it might be interesting to look at new solutions in order to make it transparent to the users how the data is first collected and also analyzed, and most importantly, what potential information could be derived by it. Finally, in our conclusion, we showed that it is possible to classify user as well as environmental characteristics when riding a bike. And the 4 characteristics that we have observed are the bike type, the gear, seat height, and terrain. And we further conducted a user study with 17 participants. The random forest classifier achieved the highest accuracies for all different categories. And again, we want to highlight that in the study, we wanted to show the feasibility to distinguish between different characteristics and between different participants in the user study, but we want to also tell again or say again that the applications that make use of these data can create fine-grained user profiles that users are often not aware of. They can distinguish between activities, and they can, in even deeper looks, also differentiate different characteristics of those activities performed. We therefore, for future work, again highlight that design of new solutions for users to allow for transparency on the data collection might be interesting and also promising. Here's a list of recommended reading. Feel free to take a look at it, and thanks for your attention. And if you have any questions left, feel free to ask. Thank you.